So today we're going to be representing a relationship, and we're going to be representing it in 4 different ways. The most basic way to represent a relationship is with a table of values. And through the table of values, we're going to create a set of coordinates and then a mapping diagram, which is going to tell us what type of relationship we're running into. And this is one of the big ways that we're going to test to see if our relationship represents a function. And then we're going to graph it and see if indeed this mapping diagram does represent a function. So each relationship must have a cause and effect. Now, this is really saying each relationship must have a cause and effect in order to be a function. You can have a relationship for anything. You can say, hey, I want to test the number of butterflies outside versus what my score on my math test is going to be. And you're going to come up with a relationship. But what you notice is that the relationship doesn't have a cause and an effect. The number of butterflies outside has no indicator of how well you're going to do on your math test, unless, of course, you're a really big butterfly fan, and maybe the butterflies give you that extra boost in order to be a really good student that day. In all reality, the relationship that you built up is not cause and effect, so therefore it's not functional. So let's go ahead and let's cross out each relationship must have a cause and effect, and let's write each function must have a cause and effect. And the other thing that we're going to be covering is because time is generally considered to be something that moves unobstructed, you'll learn if you really jump into physics later on that we can actually sort of manipulate time, and we're getting some really good leaps and bounds in development on this field. So we're just going to leave this with generally considered something that moves unobstructed. We're going to call this our universal independent variable, or our universal cause. Because time is assumed to be the passage of a lot of things, it will be the cause of a lot of actions that we see. But enough about the background, let's jump in and see what we're doing. So we have a series of pictures going on here, and what we notice is that in each picture, it looks like we have plants and we have butterflies. And so what we want to know is, we know there's a relationship that we can set up. We want to test if that relationship is functional, cause and effect related. So the 2 things that we have changing, let's go with plants and butterflies. And we're just going to record what we see, piece by piece by piece by piece. So in my first one, we have 2 plants and 8 butterflies. In my second one, I have 3 plants and I see my original 8 and 4 more, which make 12. And then the next one, we have 4 plants and see, it looks like we got 4 extra up there, so 16. And then for 5 plants, we got these big ones over here, so 20. And so what it seems to be doing is that each number is going up. And so when we go to create our coordinates, we're going to ask ourselves, does one cause the other? So let's ask the question both ways. Do the number of plants in a room cause, or let's look at it this way, does the increase in the number of plants increase the number of butterflies in a room? Or does the number of butterflies in a room increase the number of plants there? One of them sounds like it makes more sense than the other. We're going to say plants bring butterflies into a room. But if you bring butterflies into a room, that's not going to spontaneously grow plants. But having the plants might cause the butterflies. So we're going to list our plant variable first. So 2, 8, 3, 12, 4, 16, and 5, 20. Boom. So we have that. We said that the plants caused the butterflies. Now with the mapping diagram, what we're going to do is we're going to list these variables. I'm going to list all my x values. So I'm only looking at the first portion of the number. I'm going to list them in order from least to greatest. These are already ready to go. So 2, 3, 4, and 5. And I'm going to bound them up and name them. X equals the number of plants. And then I'm going to do the same thing to the other variable. I'm going to list them in order from least to greatest, of which this is already ready to go. Y is the number of butterflies. Awesome. And the mapping process simply says, let's map, if we have 2 plants, how many butterflies do we have? 8. So we're going to map that straight across. If we have 3 plants, we have 12 butterflies. And we notice each one of these maps straight across. Now what this tells us is this relationship appears to be functional. If we have 2 plants, I get exactly 1 answer. I have 8 butterflies. 3 plants, I have 12. 4, I have 16. And 5, I have 20. If I said I had 2 plants and I had more than 1 answer, that would be a non-functional relationship. And so let's go ahead and let's graph this. Now, because all of our variables are all positive numbers, we're going to go ahead and we're going to put our axis on the bottom of the graph. And this is going to give us some room for all the positive numbers. We could put it right in the middle, but we'd be wasting all the negative space. So I just took that, I moved it all the way down. That gives us all the room that we need for positive numbers. Cool. And then we do the same for the y. I'm dealing with all positive x values, so I'm leaving all the room for the positive numbers. I could put the axis in the center, but I would be losing all the space over here because I'm only going to be looking at the right half of the graph. So again, just move it over. It gives you more room. Okay, so we know our x values are going from 2 to 5. I got plenty of room, so those are going to be listed by 1s. The y values are going to 20. So what we're going to do is we're going to say, hey, we're going to count each y worth 2. And that's going to give us an excuse to fit everything on this graph. And so when we graph this, we're going to graph our coordinates. So 1, 2, and then 2, 4, 6, 8. This isn't 2, 4, because remember, our x's we're counting over by 1s. So 1, 2, 3. And then I'm going to count up by 2s to 12. So 2, 4, 6, 8, 10, 12. Count over 1, 2, 3, 4 by 1s and count up to 16 by 2s. 2, 4, 6, 8, 10, 12, 14, 16. Count over by 1s, 2, 3, 4, 5, and up by 2s. 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. And what we're going to do today is we're going to check to see, is the relationship linear? Which means that we're going to take a ruler and we're going to attempt to draw a straight line through every one of our points. And it looks like we were successful, which means our relationship is linear. Not only is it linear, it's positive linear. So it's going up, which is going to be necessitated by this mapping diagram. So let's try one more. What we've got going on here is it looks like we have 2 things that are changing. Looks like I have donuts and a bill. So let's put donuts and the bill. The first one we had 2 donuts and a bill of $3. The next one we had 5 donuts and a bill of $7.50. Here we had 8 donuts and a bill of $12. The last one we had 3, 6, 8, 10 donuts and a bill of $15. Probably don't need all those decimals, so when we do the coordinates, we're going to cut off the decimals. But let's ask, when we're trying to figure out cause and effect, do an increase in the number of donuts cause the bill to increase? Or does an increase in the bill cause the number of donuts to go up? And so you could really make an argument over both here, but given this scenario, the only way that we see the bill going up is by donuts. We could get the bill to increase by buying like a soda, but we don't see any evidence that this company sells sodas, so we're not really sure how we could get the bill to go up without increasing the donuts. So the donuts are going to be the cause here. We have 2, 3, listing the donuts as the first number, meaning they cause the bill to change. 5 comma 7.5. Again, we're cutting off the decimals that we don't need. 8 comma 12 and 10 comma 15. The mapping diagram, we're going to do our two-part map, which means we're going to take the x values, 2, 5, 8, and 10, and list them in order from least to greatest, and label them. X is the number of donuts. And then we're going to do the same for y, in order from least to greatest. Bound them up. Y is the bill. And when we map them, we notice that this also maps straight across. Each one of these goes directly across. So we should see the same type of relationship as before, something that's going up. As one is going up, so is its partner across the way. So let's graph this. We're dealing with all positive values, so we're going to put the axis on the bottom and on the left. I'm dealing with numbers 1 to 10 for my x, so that works fine. So x is by ones. I'm going to 15, so let's do the y by 2s. That should give us plenty of room. And graph them. So we're going to count over by 1, 1, 2, and up by 2s, 2, and almost 4. Over by 1s, 2, 3, 4, 5, up by 2s, 2, 4, 6, almost 8. So I'm going to put it right at the top right there for 7.5. 1, 2, 3, 4, 5, 6, 7, 8, and up 2, 4, 6, 8, 10, 12. Right on the point. Then all the way over to 10, and up 2, 4, 6, 8, 10, 12, 14, almost to 16, but halfway there. Awesome. So we're going to take this line, or take this graph, and we're going to check to see if it is a line by taking 2 points, so these 2 points, and drawing a line through them, and seeing if I hit all my other points. And we did. I was a little off right here. That's mostly due to my drawing error. That's not due to the graph being off. So boom, we see another upward graph because we have a direct relationship. As one goes up, so does the other. And also, this is what we call a linear relationship, meaning it forms a straight line. So let's go ahead and let's check out a few more. Here we have a cat who's on a scale and some cans of tuna. So it looks like the cans of tuna are changing. The cat looks like it's getting a little wider, which if we look a little closer, yes, that scale is actually increasing. So we're going to say the cat's weight and the tuna are the two things that are changing. And so in the first one, this cat's weight looks like it's 2 tick marks over. And then it goes to 4 tick marks, to 6 tick marks, to 8 tick marks. The cans of tuna go from 4 to 6, 4, 7, 8, to 8, 4, 7, 9, to 10. Cool. And so again, ask yourself, do we think that the tuna causes the cat's weight to change? Or do we think the cat's changing weight causes the tuna cans to appear or disappear? Well, that one's a little easier to kind of judge, unless you're thinking of it from the cat owner's perspective, meaning a fatter cat might demand more food and you might go out and buy more food. So you could realistically make an argument for that point, but we're going to say the more tuna you feed the cat, the fatter it gets. So let's go ahead and list the tuna first. So 4, 2. This is unlike the ones we did previous where we just listed them in the same order. Remember, we always list the cause or what is causing the other variable to change first. So 6 comes before 4, 8 comes before 6, and 10 comes before 8. Awesome. And so now we're going to list our mapping diagram from least to greatest. So 4, 6, 8, 10. X is the cans of tuna. And then we do the same for Y. So 2, 4, 6, 8. And Y is the cat's weight. And when we map these, again, we see a direct relationship straight over, which means that as one variable is going up, so is the other. So we're expecting to see another positive trend. In fact, if we graph this, these both fit on a 1 scale. So what we have right here is we have 1, 2, 3, 4, 2, 5, 6, 3, 4, 7, 8, 5, 6, 10, 7, 8. We notice that this gives us the direct relationship we were looking for. The line is going up, and they all connect with a straight line, which means this graph is also linear. Awesome. So what I want you to try and do is I want you to try this last one. Now, this last one may be a little small if you're trying to watch in the video. Right now we have a clock that is at 12, 2, 3, and at 5 in case you can't see. And our account balances are 50, 68.5, 77.75, and 87 even, along with anything else that you can spot that is changing. But give that a shot and see if you can't find 2 variables that are changing, see if you can't form a relationship, and resume it when you're done. Okay. So unfortunately, because I did have to read you off these things, it kind of clued you in on the 2 things that are changing. We have time and bank account. So our account balance and the clock. And now the reason why I put this in here is because we're going to see something's going to go on with time. And you may have experienced a little wonky graph right here that you're like, well, it's not linear. Let's take a look what's going on. At $50 in my first one, I had $68.50 in the second one, $77.75, and then I had $87 even. At the first one, it was 12 noon, so let's call that 12:00. The second one, we have at 2 o'clock. Now, what a lot of people will do is they'll put 2 o'clock. But let's ask, from 12 to 2, did time move forward? Well, your answer should be yes. But if I look at here, what happened with my x's? Did my x's move forward? Well, the answer is no. We actually went from, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We went from 12 all the way back to 2. And so we run into a problem right here. We know that 2 won't work. And so is there a way to move from 12 to 2 o'clock without moving backwards? Well, there is if you consider military time. Now, if we know 12 plus an hour would be 1 o'clock, 1 o'clock would be 13. And if I add another hour, 2 o'clock would be 14 o'clock. So boom, I have a way to add time to 12 o'clock and still get my 2 o'clock swing right there. So that is 14 o'clock this cashier has $68.50. At 3 o'clock, we're going to add another 100, so that would be 1,500. And then at 5 o'clock, let's see, 1,600 and 1,700. So 1,700 is 5 o'clock, but it's 5 o'clock in the evening. Perfect. And so there's two ways to consider the scenario. Do we think that the passage of time causes the bank account balance to go up? Or do we think the increase in the bank account balance causes time to pass? Well, if you're looking at it from the shopper's perspective, the more time we spend, the lower the bank account balance would go. So we must be the cashier, which I did mention a little earlier. But our bank account balancing changing doesn't mean time has passed. We don't know what's going on with the bank account. But the passage of time, as long as you're working, means that you're getting paid by the hour. And also, if we remember what we mentioned earlier, time is generally considered to be the universal cause or the independent variable. So if given the option, always take the passage of time and put that first. So we're going to list that first, and we're going to list the partner second. Boom. And then we're going to go through and list these in order from least to greatest. So 1,200, 1,400, 1,500, and 1,700. X is the hours in military time. Then we're going to do the same for the Y's. 50, 68.5, 77.75, 87. These are in least to greatest, and Y is the account balance. And when we map these, we get a direct straight across relationship, which means that as one is increasing, so is the other. So we're expecting to see another upward trajectory. Okay? So all positive values. So I'm going to draw my axis down here and over here. My X needs to go up to 1,700. So I'm going to have to make my X worth 200. My Y needs to go up to 87, so we're going to make our Y by 10s. Let's take a shot and see what this looks like. So 2, 4, 6, 8, 10, 1,200. We were at 50, so 10, 20, 30, 40, 50. At 1,400, so 1,200, 1,400, we were at 68.50, so almost 7. 10, 20, 30, 40, 50, 60, almost 70. Put that right there at the top. Another hour later, so 14 halfway over is going to be 15. And if that's 70, then that must almost be 80. And then 17 o'clock, so 2, 4, 6, 8, 10, 12, 14, 16, almost 17, so in between. And if that's almost 80, this will almost be 90. And when we connect these with a straight line, boom, we know that this is a linear relationship. And there we go. So today we're going over the second part of representing a relationship. This is going to be, now I got a little overly excited about this. This is actually not an inverse relationship. This is what we call a direct negative relationship, whereas the previous one we had a direct positive relationship. And now this happens when you see one variable increasing while the other is decreasing. An inverse means while one is getting larger, one is getting smaller. It's a very slight wording difference, but again, got a little excited, so let's just fix this. This is a direct negative relationship, which means that as x is increasing, if you have your variable x and as it goes to the right, y is increasing, which means that you have y is decreasing, which means you have a negative relationship. And vice versa, as x is approaching negative infinity, as x is going in that direction, so directly to the left, y is approaching positive infinity, which means the line is going up in that direction. So again, you have a line that's going perfectly straight, but it's going down. So let's take a look at a few of these. Like before, we're looking through these photos and finding two different things that are changing. Here I see the level and I see a grade as two things that are changing. Perfect. And so on the first one, I see that we have a level 1, we have a level 3, a level 7, and a level 9. When we got to level 1, we were at a 98, then we were at an 84, and then a 56, and then a 42. So whatever type of level is going on, the higher the level we go, the lower our grade is going, or that seems to be the cause, which answers our next question, is do we think the level is the cause of the grade change, or do we think the grade change is the cause of the level? Well, I'm looking at this and I am seeing what looks like a television, so I'm assuming this is a kid playing video games, which means the longer he's playing video games, the less time he's spending studying. So we're going to say that the level causes the grade. So we're going to list this left column first. Perfect. And so when we do a mapping diagram, we remember the fact that we always list the mapping diagram in least to greatest. So just like that, 1, 3, 7, 9, and I bound it up and I label it. And then we do the same to the other side. Least to, this is in the reverse order. So least to greatest, we're going to have to start with the bottom and work our way up. So 42, 56, 84, and 98. And so y is the grade. And now when we bound this up, we notice that 1 is connected to 98. So I'm actually going to be going down. I'm not going straight across like we've done previously. 3 is also connected to 84, 7 is connected to 56, and 9 is connected to 42. And so what we notice is we've created this like starburst pattern. And this starburst pattern is indicative of a negative relationship, which means that as one is increasing, their partners are decreasing. So we should be seeing a different type of line here in just a second. Now my x value, these are all positive numbers, so I know I can go ahead and put my axis down here at the bottom. These are all positive numbers, so I can also put these on the left. Actually, should have said that in the other direction. These are positive, so I put that on the bottom. These are positive, so I put that on the left. These fit 1 to 10, so my x is by ones. These go up to 100 almost, so I'm going to do my y by tens. Let's see what this trend looks like. See, I go over by 1 and go almost up to 100. I go over by 3 and I go up to 80 and about halfway. So 3, 4, 5, 6, 7, and I go up to 56. So 10, 20, 30, 40, 50. We're going to put 56 right there. And then 7, 8, 9, 10, 20, 30, 40, and 42. And if we connect these, any 2 points, I'm going to connect these 2 points right here. We notice that they all connect, albeit it is direct negative. Like we said, this is still a linear graph. Awesome. So if we do another one of those, we're going to look at this. Number 3. Looks like we have flies around fruit and a fly swatter and a couple different types of fruit here. And as we move over to the next picture, it looks like we have a new fly swatter and we still have a bunch of flies. And let's keep going. Now we have 4 fly swatters and okay, so we see what's going on. The more fly swatters we have, the fewer flies we have. Or the fewer flies we have, the fewer fly swatters, or the more fly swatters we'll have. So I think we've just answered our cause for the coordinates, but we're going to start out with the number of flies and the fly swatters. So fly swatters in this one, I had 1, I had 2, then I had 4, and then I had 6. The flies are going to be a different story. Let's go ahead and try and count these. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30. We had 30 flies. Next one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then the last one we have 1, 2, 3, 4, 5. Perfect. So we ask ourselves what causes what? Well, lowering the flies don't decrease the fly swatters. If anything, the increase in the flies should increase the number of fly swatters we have. But to do what? Well, to get rid of the flies. So it looks like the more fly swatters we have, the fewer flies we have. So let's list fly swatters first. Boom. And then their adjoining number of flies second. It sounds like this is a test to see how useful a fly swatter is. So you really should, if you make fly swatters, use this as an ad. Hey, more fly swatters you get, the less flies you have in your house. I would buy that fly swatter. Mapping diagram, we're going to list our x values on the left from least to greatest. And our y values on the right from least to greatest. And we're going to go ahead and we're going to map them. And just like before, we notice that as we map these, we create a starburst pattern, like a little spider web in the middle. And we notice that that means that as one is going up, the other must be going down. So that's going to help us with our graph. All positives. So our axis is down here and over here. 1 to 6, so my x is by 1s to 30. So let's do our y by 3s. If we graph this, 1 pairs with 30, so all the way up. 2 pairs with 15, 3, 6, 9, 12, 15. Oh, 1 pairs with 30, 2 pairs with 25. So ignore that point. 3, 6, 9, 12, 15, 18, 21, 24. Just above 24. I made the universal mistake of trying to read straight across. Remember, this is not a straight across method. We pair them up, or we could probably just read these over here. So I'm going to skip reading this and just go straight to that. 3, 4, 3, 6, 9, 12, 15, 5, 6, Boom. And so we see that that little point would have screwed up our graph, but we saved it. And so if I connect any 2 points, we're checking to see, does it create a linear relationship? And this, in fact, is linear because we form a straight line. There we go. And so let's take 2 more problems. What I want you guys to try is I want you to try numbers 5 and number 7. I want you to see if you can't come up with some sort of variable change and see if you can come up with either a positive or a negative relationship, therefore. So pause the video, resume it when you're done, and see how well you did on numbers 5 and number 7. Okay, so at this point, we should be pretty good. We notice in this one, the number of plates is going up. We also notice that our weightlifter seems to be losing a little bit of weight in his torso and gaining a little bit of weight in his arms, which means we're assuming he's getting stronger and more fit. And so outside of taking a ruler and saying, well, how wide is he? We have a way to measure that right below him. He's wearing a belt. And it looks like he has either 1 notch or 3 notch. He's getting smaller, so let's go ahead and see which one's getting smaller. The one on the left turns into 2, that got bigger. The 3 turns into 2, so that's getting smaller. So I'm going to go with the numbers on the right. So notches on right. So when he had 1 plate, he had 3 notches. 2 plate, he had 2 notches. 3 plate, he had 1 notch. And at 4 plates, he has no notches left. He's about to need a new belt. We ask ourselves, does increasing the plates lose the weight, or does losing the weight increase the plates? Well, just losing weight doesn't mean you get any stronger, but getting stronger does mean you might lose some of that excess weight. So we're going to say the plates are going to be listed first. So we're going to list the left column first. That's a 2. If you really believe that's a 2, that's a 2. 4, 0. Boom. And if we list our mapping diagram, we have 1, 2, 3, 4. And for our y values, opposite orders, 0, 1, 2, 3. Y is the notches on the right. And when we map them, we notice that we're creating that very intricate spider web. Boom. So we know it's a negative relationship. So we're going to graph our value right here and right here because we're dealing with positive numbers. Looks like both of these can be done by 1s because we're dealing with relatively small numbers here. We're dealing with 1, 3, 2, 2, 3, 1, and 4, 0. Well, that's a very short and very close line. Boom. Exactly what we thought. A negative linear relationship. Perfect. And if we take a look at number 7, if you've already tried that one, what we notice is it looks like we're driving. We notice that the mile signs are increasing piece by piece by piece. So let's see, our mile signs went from 26 to 111 to 196 to 281. And then if we look at the cart, we're going the same speed. We're not turning, but our fuel gauge seems to be dropping. The other thing here is I don't actually have a number, so I'm going to have to list a full tank. whatever our full tank is. Well, for me, I'm going to use my own personal car. And I'm going to say, well, my tank has about 13 gallons because it's a little car. And I know here is about halfway. So half of 13, we'll say that is, let's round up. Let's say that's 7. This is about a quarter. So a quarter of 13 is going to be just, let's say 4. We're going to round up again. 3.5 rounds up to 4. Which means that if I add 3 to get to that 3/4 mark, I must be at around 10. Perfect. Okay. We ask ourselves, does driving cause our tank to go down, or does our tank going down cause us to drive? Well, if you live in the South, you know your tank will go down without driving because that AC unit will use up that gasoline. So we're going to say the miles actually cause the tank to go down. So 26 is before the 13. Boom. We make a mapping diagram. List our y values, reverse order, because it's always listed least to greatest. So we're going to say tank gallons. And when we map it, we again notice that as we travel on, we get less and less gallons. We've created a negative relationship. Let's go ahead and see what that graph will look like. X goes all the way up to almost 300, so I'm going to say this is by 30s. Y only goes up to 13, so if I did my Y by 2s, that should be good. Let's see. So 26, we're at 2, 4, 6, 8, 10, 12, 13 gallons-ish. Then at 111, so 30, 60, 90, 120. So somewhere right here, we are at 10 gallons. So 2, 4, 6, 8, 10. 196 miles, so 30, 60, 90, 120, 150, 180. Somewhere in here, we're at 7. 2, 4, 6, 7. Then at 281, so let's start over here, 300, 270, so in between the last digit, we're at 2, 4. So we notice that as we keep driving, our tank is going down. We could actually use this if our graph went out far enough to predict when we're going to run out of gas. So we've created a negative relationship that does form a straight line. And there we go. So today we're going to be representing a relationship that is nonlinear. This is the third part in the series of representing different types of relationships. So far we've graphed linear lines going up and negative lines going down. Now we're going to be graphing nonlinear graphs. And so quite literally that just means they don't make a straight line. There's going to be 2 types of graph that we're going to cover. For this video, it's not important to be able to tell every single time what types they are. I will provide that for you. But really in a future lesson, we're going to go over much more in depth how to recognize what each type of line is. But for now, we're going to say that they are nonlinear. So let's jump in. In the first series of videos, it looks like we have a guy that appears to be skydiving. He's in the plane, he's below the plane, he's well below the plane, and then he keeps falling. We're given an altitude and a recording time. So let's go ahead and do that. The altitude in the first video is 10,000 feet. Then we're at 9755. Then we're at 9020. And then at 7795. So it looks like the gaps are getting bigger and bigger. So let's look at the time. The time was at 0, and then at 5, and then at 10, and then at 15. And so you might ask yourself, if you're used to graphing linear graphs, is that, well, if I'm increasing by 5 each time, why is this not consistent? And this is going to be what we call a quadratic graph. What we notice is that each second, the faller is falling at an increasing speed. Gravity's pulling on him more and more and more. So speed is increasing. So let's take a look. We're going to create a series of coordinates. We know that time is the universal independent variable, so we're always going to list time first if we can. So I have 0, 10,000, 5, 9, 7, 55. I have 10, 9, 0, 2, 0, 15 at 7, 7, 9, 5. Awesome. We're going to create a mapping diagram, which means that we're going to take the left values and list them in order from least to greatest, bound them up and label them. And y is going to be listed from least to greatest. In this case, looks like it's upside down. Bound them up and label them. Y is our altitude. Now what we notice is, like in one of the prior videos, when we start mapping which one is 0 connected to, it's the bottom one. 5 is the second bottom one. 10 and 15. We've created a starburst pattern. We've seen this pattern, and we know that that means it is a negative relationship, which means the graph is going down. Now, we notice that it's not going to be a straight line, but we do know the graph should have a downward trajectory in some way, shape, or form. Something is happening. As of right now, we have nothing but positive values, so I'm going to put my two axes on the left and on the bottom. Go to 15, so I'm going to make my x by 2s. And I go to 10,000, which means my y is going to be by 1,000ths. Awesome. My first point at 0 seconds is all the way up at the tip of the top at 10,000. My next point, 5, is at almost 10,000. It's at, let's see, 2, 4, 5, is going to be about 3/4 of the way up. And 2, 4, 6, 8, 10. We're going to be at 9, so just over 2, 4, 6, 8. 2, 4, 6, 8, 10. We're going to be right here, just above 9. I kind of drew mine a little below 9, but that'll make the point. 2, 4, 6, 8, 10, 12, 14, and then this is going to be 15. We're at 1,000, 2, 3, 4, 5, 6, 7, 7, 7, so it's going to be right there. And now this is what's going to clue us into it's a non-linear function. If we try and connect any 2 points on this function, if I try and connect these 2 points, I'm not going to get all of my points included. If I try and connect these 2 points, I'm not going to get the 2 ends. I'm going to miss and I'm going to miss. And if I try and get, let's say this one, or these 2 points, I'm going to miss the 2 in the beginning. So no matter which line I draw, I don't hit all my points. So we know the fact that this line is what we call nonlinear. In fact, in a later lesson, what you'll do is you'll figure out, using this table of values, you'll learn that this is not only a nonlinear function, but a quadratic. And we'll learn about those in a future video. Okay, so let's go ahead and let's try another one. Let's try this one. Now this one, it looks like we have some plants popping up, and it looks like we have a calendar here that's going through. So I'm going to go ahead and say plants and the date. Looks like we have 3 plants on the 9th. 1, 2, 3, 4, 5, 6 plants on the 16th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 plants on the 23rd. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And we have 24 plants on the 30th. We know that the date is a time factor, so we're always going to list the date first. So 9, 3, 16, 6, 23, 12, and 30, 24. What this means is that the passage of time causes the plants to grow. Plants growing don't cause time to move. It may imply that time has moved, but it doesn't cause time to move. And so when we map 9, 16, 23, 30, X is our date. And then for our Y's, we have 3, 6, 12, and 24. Y is our number of plants. Okay. We notice this one, unlike the first one, is a direct across relationship, which means that as this variable is increasing, so is the other, which means we're expecting some sort of a positive trend to happen here. So let's take a look. See, we have nothing but positives on both variables. So we're going to list our axes. On the bottom and on the left, I'm going to 30 over here, so my X is going to be by 3s. And I'm going to do my Y by 3s as well, because we're going to 24. Perfect. So if I go by 3, 6, 9, 3, 3, 6, 9, 12, 15, just beyond that, I'm going to go up 3, 6, so that's 15, 18, 21, 24, so just before that. So that's 24, 27, 30. So 3, 6, 9, 12, 15, 18, 21, 24. Boom. And again, what we notice here is that no matter what 2 points we use, when we try and connect them, I miss the other 2. And this is a little more exaggerated than what we had before. What we notice is that no matter what 2 points I connect, I can't hit the rest of my graph. So this is not a linear graph. This is not a straight line. This is non-linear. And in fact, this is a very special kind of non-linear. It's called an exponential. E-X-P-O-N-T-I-A-L. Ignore that weird looking N that I just drew right there. And exponential graphs are pretty easy to spot because if you notice 3, 6, 12, 24, we're doubling each time. So later on when you cover exponentials, just notice that your values are either doubling, they're tripling, or they're being cut in half continually. So let's try a few more. So looks like we've got numbers 5 and number 7. What I want you guys to try is I want you to pause the video, try number 5 and try number 7. See how well you did. Unpause the video when you're done and give it a shot. Okay. So on number 5, what looks like's going on is we have a pizza. So pizza slices. I've also got this handy dandy thing down here in the corner with a timer. So it looks like here we have 8 slices. We have 4, 2, and 1. So just like before, we already know, because this is being cut in half each time, this is going to be an exponential graph like we just covered. But we're going to go ahead and we're going to do the rest of this just to kind of prove that that is the case. And I have a 6-hour, 4-hour, 2-hour, and just now. So we're going to have to interpret this and say, okay, so it looks like when I see 6 hours, I had a full pizza. At 4 hours, I had half a pizza. So unless it's taking us 2 hours to make a slice of pizza, we're going to assume that this is in reverse order and we're eating the pizza as it goes. So this isn't 6 hours in the future, this is 6 hours in the past. So we're going to represent that time by a -6. Just like this isn't 4 hours in the future, this is 4 hours in the past. So -4. Here we have a -2, and just now we're at 0. And again, we generally list time as the universal independent variable, so we're going to list the -6 first before we list the 8. The -4 before we list the 4, the -2 before we list the 2, and the 0 before we list the 1. When we go to map it, least to greatest, already in the correct order. Then we're going to list this in least to greatest, which is in the reverse order. Perfect. And when we map this, we notice that we create a starburst pattern. Boom. So with the starburst pattern, we know it's going to be some sort of a downward trajectory. Now, our x values are all negative. So what I'm going to have to do in order to account for the x values, instead of leaving it on the left for all the positives, I'm going to move the axis to the right so we have all the negatives. So this is the case where our axis has moved to the other side. The y values are all positive, so we can leave the x-axis on the bottom to give us all that positive room. So x is still by 1s, and in this case, y can also be by 1s. Graph this, -1, 2, 3, 4, 5, 6. We had 1, 2, 3, 4, 5, 6, 7, 8 slices. 2 hours later, we had 7, 6, 5, 4 slices. 2 hours later, we had 2 slices, and 2 hours later, we had 1 slice. We notice that when we try and connect to these points, just like we said earlier, we can't actually connect them all with a straight line. We end up missing most of the points. So this is what we call nonlinear. It's a very special type, exponential. Boom. Awesome. You may have used the comments, in which case you got a direct linear relationship. For every 2 hours that passed, we got an additional comment. On the last one, we noticed that it looks like what's going on is we're having a tournament here. Looks like each round we have 2 countries that are facing off and we have a winner. So looks like, cool, we have the US faced, I believe this is Australia, and the US won. And then in the next round, the US faced France, and France won. So that's why you see some flags listed more than once, boop, 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 and some flags stop, so boop, boop, and not the next time. This one didn't even make it the first round. So let's go ahead and let's break this down. So we have rounds, and we have countries. So on here, it looks like the first round's already done. We're on the second round. And there are 1, 2, 3, 4, 5, 6, 8 countries left. Here we're on the first, second, third round, and there are 4 countries. 1, 2, 3. We're on the 4th round, and there's 2 countries, and the last one is the 5th round, where we have the 1 winner. So whatever this is, Germany has won. Let's go ahead and build this as a coordinates. Rounds are going to dictate passage of time. So we're going to list the rounds first. So 2, 8, 3, 4, 4, 2, and 5, 1. We're going to do a mapping diagram. It's in the correct order. So 2, 3, 4, 5. And this is in reverse order, so 1, 2, 4, 8. We notice that this is getting cut in half each time, so it's going to be just like before. We're going to have an exponential graph. And just like before, what we notice is that when we had 2 rounds in, we had 8 countries, and every time we went up a round, we lost half the countries. So this is going to be a negative relationship. It's going down. Should be quite similar to this up here. Unlike that up there, though, we have all positive numbers, all within 1 to 10, which means that we can do each of our axes by ones, and we can do them on the bottom and on the left. So if we go 2 rounds, we were at 10, 9, 8 countries. At 3 rounds, 7, 6, 5, 4. And then we were at 2, and then we were at 1. So technically speaking, this would keep going, but we know at this point, this graph kind of stops. But regardless, we know that if we try and connect 2 of these points, we're not going to be able to connect our entire graph. So no matter which 2 points, I won't get all the points. So we're going to call this one non-linear. In fact, it's the very special kind called exponential. Boom. We don't need to know that part. We just need to know that it is non-linear. And there you go. So this is the 4th part of representing a relationship. What we've got going on here is we're most often addressing the mapping diagram portion of the relationship mapping. This means that we're pretty good on table of values and coordinates, but what we often see is we see people just list the coordinates in whatever order they're listed in. They're not actually mapping them from least to greatest, so we're not getting that trend to see what type of relationship we're dealing with, whether or not it is a function, which is the whole point of a mapping diagram. So let's go ahead and get started. Now, each of these is out of order. So we're going to be forced to assemble them in order right here. So on number 1, it looks like I've got cows and looks like canisters. I'm going to assume those canisters are jugs of milk because that's what cows make, is they make milk. Or we could go with jugs of butter, but we're going to go with milk. So here I have cows and milk jugs. I had 4 cows, and we had, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. We had 16 jugs of milk. Here we had 2 cows and 4 jugs of milk. We had 1 and 1. We have 3 cows and 1, 2, 3, 4, 5, 6, 9 jugs of milk. Now the coordinates, in this case we know cows make milk, so the cows are going to be the cause. So 4, 16, 2, 4, 1, 1, and 3, 9. The mapping diagram in here comes into play, is we always need to list them least to greatest. So it's not just listing them directly or indirectly, we have to sort. So it's 1, 2, 3, 4. 1, 2, 3, 4. And X is our number of cows. Our Y values, again, we're going to have to sort them. 1, 4, 9, 16. Jugs of milk. Perfect. And if we map these, we notice that 1 maps with 1, 2 maps with 4, 3 with 9, and 4 with 16. We have a direct positive relationship. And so, because these are all positive numbers, I can put my axis down here at the bottom. left. I'm going 1 to 4, so I can do my x by 1s. 1 to 16, so we're going to do our y by 2s. We graph these. Let's see, 1, 1, 2, 2, 4, 3, 2, 4, 6, 8, 9, 4, 2, 4, 6, 8, 10, 12, 14, 16. And we notice, albeit that looks like it almost could be a line, if we try and connect any two of the dots, we notice that, albeit it starts to get closer, we don't actually hit any of these values. So this, because it's approaching a line, it's nonlinear. And this is actually a very special type of nonlinear that we call a quadratic. Perfect. Okay. And if we try number 3, let's take a look at this. So it looks like we have some ducks at a crosswalk and some cars in the background. Yep, and it looks like the ducks are walking across in some order and the cars are piling up behind them. So let's go ahead and make this the number of cars and the number of ducks. Okay, in here I see 1, 2, 3, 4 cars, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 ducks. Here we have 3 cars and 1, 2, 3, 4, 5, 6, 7, 8, 9 ducks. We have 2 cars and 1, 2, 3, 4, 5, 6 ducks. 1 car and 2 ducks. So you may or may not want to count the mama or daddy duck, but I just counted them all. Okay? And so let's take a look here. Now, do the cars cause the ducks to add up, or do the ducks cause the cars to add up? In this case, the ducks are causing the cars to add up. You may be able to make a case for the other one, but I don't think increasing the number of cars will increase the number of ducks. If anything, it may decrease the number of ducks because more cars on a highway mean that the ducks are more likely going to get hit. So we're going to go with the positive way of interpreting this. More ducks on the road means there's more cars because they're waiting for the ducks to cross. So we list the ducks first. Perfect. And when we do our mapping diagram, we do the left numbers from least to greatest. So 2, 6, 9, 13. Then we're going to list the y's from least to greatest. Cool. And if we map them, 2 mapped with 1, 6, 2, 9, 3, 13, 4. That's a direct positive relationship. If we graph them, we have our x-axis down here and our y-axis down here because we're dealing with nothing but positive numbers. I'm going to have to do my x by 2s because I'm going above 10. My y is going to be by 1s because I'm dealing with numbers below 10. We're going to go ahead and we're going to graph this. So 2, 1, 2, 4, 6, 2, 2, 4, 6, 8, 9, 1, 2, 3, 2, 4, 6, 8, 10, 12, 13, 1, 2, 3, 4. And if I try and connect any 2 points with a line, let's see. Ooh. That looks perfect. So we know that this graph is in fact linear. Perfect. Let's try a few more. So what I want you to try is I want you to try numbers 5 and number 7. Pause the video, unpause it when you're done, and see how well you did. Okay, so what looks like going on is I have some sort of a pen happening here, and it looks like the sun is either rising or setting. So I could go with the height of the sun, but I'm going to assume the sun is a passage of time. And it looks like the rabbits are changing here. So let's take a quick look. So I'm going to come back to the sun here in just a second. I'm going to count the number of rabbits. So here we have 8, 4, and the last one is 2. If I count this middle one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So we have 16 rabbits. So with those 16 rabbits, we're going to look at the sun now. Now, here, we said it was either rising or setting. If it was setting, that means this is going to be the first time and we have the most rabbits. And then we have fewer and fewer and fewer. So either the rabbits are getting out, or we can look at it the other way, and it's rising. So we have 2, then we have 4. So it looks like they could be breeding. So albeit, I don't think rabbits are breeding that fast, we're going to go with the rising sun. Just because more rabbits, if the rabbits are getting out, that's sad. So we're going to assume that these rabbits are breeding at an astronomically fast rate. So I'm going to assume that this sun is going to rise at, let's say, 6 a.m. Oop, wrong spot. This is the last unit. So 6 a.m. for that rise. I know it looks like the second one, it went up by about half a sun. So realistically, that would be, I'd say like 6:15. But we're going to kind of do a little cheaty method and say that that is at 7. And then we notice that it looks like it's rising at about the same rate. So I know that that would be an 8. Hey, perfect. I can use my scribble to our advantage. That's an 8, which would make that a 9. Time is always the universal independent variable, so I'm going to list that first. Perfect. So that way when we do a mapping diagram, we say, okay, 6, 7, 8, 9, list them in order from least to greatest and bound them up. And the y-axis, least to greatest, so 2, 4, 8, 16. Perfect. And if we map them, 6 with 2, 4, we have a direct relationship. This should be positive. So let's go ahead and let's graph this. All positive numbers means that the axis can be on the bottom and on the left because that deals with the natural numbers. All the way to 10, so I'm going to say my x is by 1s, all the way to 16, so we're going to say our y is by 2s. Perfect. So if I go, let's see, 1, 2, 3, 4, 5, 6, I go up to 2, at 7, that's at 4, at 8, it's 8, and at 9, it's 16. So we notice that this graph is doubling. So we know the name of this type of graph because none of these actually connect. No matter which 2 points we use, they don't connect. This is nonlinear. If you wanted a little extra, this is actually called an exponential graph. Double, 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 double. Perfect. And then if you looked at the last one, what it looks like is going on is we have some people that are really cold and they're hanging around some fires. We've got some snow coming down as well. Snow doesn't look like it's changing very much. Maybe there's a few, but looks like they're pretty much consistent piece to piece. So we're going to go with the number of fires and the people. And so here we have 2 fires with 3 people, 1 fires with 1 person, 4 fires with 1, 2, 3, 4, 5, 6, 7 people, 3 fires with 1, 2, 3, 4, 5 people. Perfect. And let's take a look. Now, this could realistically be argued 2 ways. We could say that more fires means more people, Maybe they're coming in because they're like, I'm cold and I see the fires. Or maybe more people mean more fires and they're like, hey, I'm cold, let's make another fire. So you could really do this either way. We're gonna say more people make more fires because a fire doesn't just pop up in the snow. So I'm gonna list the people first. So 3 comes before 2, 1 comes before 1, 7 comes before 4, and 5 comes before 3. You might do it backwards, that's A-okay. We're gonna say that people make fires. List this from least to greatest. So I see a 1, 3, 5, and 7. X equals the number of people. And Y is 1, 2, 3, 4, the number of fires. And when we map it, we notice that we map a direct relationship right across. So because we're dealing with positive numbers, I'm going to draw my axis down here, down here. 1 to 10 all the way, so my X is by ones, and my Y is by ones. Okay, so 1, 1, 3, 2, 4, 5, 3, 6, 7, 4. Ooh. Looks like when we got this, that is going to be a straight line or a linear relationship. And there we go. Okay, so today we're going to be graphing functions. Now, these functions are all linear functions, and this is based off the idea that we're going to be evaluating out this function as though we don't know what the function shape is. And graphing any function takes 4 steps. The first step, when we have a function called f, we need to plug in values for x. So we need to make a table and pick values that we want to plug into this. So we're going to say x and f of x. And remember, f of x is our answer, which most of the time we're going to look at as our y. So f of x and y are going to be the same thing. This is an x, y table. And we're going to take several values. In this case, we're going to take -3, -2, 1, 0, 1, 2, and 3. Several values, and we're going to plug it into the equation. Now, if we said we were plugging in -3, I would rewrite this equation and say 6 times that -3 plus 2, which would then be evaluated out. 6 times -3 is -18 plus 2. -18 plus 2 is -16. And I would do that out for each one of these. So let's get this ready to go and write this with a blank for each number we're about to plug in. So 6 times blank plus 2, 6 times blank plus 2, 6 times blank plus 2, so on and so forth. And we're going to evaluate out each one of these to get a good picture of what's going on with this graph. We're going to plug each one of these in. So I plug in the -2, the -1, the 0, the 1, the 2, and the 3. As we work them out, 6 times -2 is -12 plus 2, which is -10. 6 times -1 is -6 plus 2, which is -4. 6 times 0 is 0 plus 2. And we work each one of these out. Almost caught up on that one. Perfect. And now, a lot of times, students will look at this and be like, what do I use for my y? So one of the things that we're going to be doing is we're going to be condensing this table down to the values we're going to use, which consists of copying down these values over here. I haven't changed my x's at all. And we're going to copy down our final values of y. Those are the values we're going to use, so I'm going to copy them down onto the table over here. Perfect. And this is what I'm going to graph. So we've taken our values, we've plugged them in, and we've solved. So we've actually completed step 1 and step 2. Step 3 is find a scale for your x and for your y that fits all of your data. I notice my x's are about even on the positives and negatives. So I'm going to go ahead and I'm going to put my axis right in the center of the graph. And what this allows me to do is this allows me to have some negatives and some positives in about equal proportions. My y's also, if I count them up, I have 3 negative y's and I have 4 positive y's. And it looks like they're about spaced out evenly. I have a negative 16 and a positive 20. Those are almost the same thing. So I can go ahead and I can put my x-axis right here, which separates about the same amount of positives and negatives. And then I need to find the scale for the x. So can I fit negative 3 and positive 3 by counting by ones? Yes. So my scale for my x's is by ones. When I check my y's, I need to go down to negative 16 and up to positive 20. Now, because they're both 5 above and below, I need to fit them both. I can't fit by ones because I'll only make it to 5. If I went by 2's, I'd only make it to 10. 3's, I'd only make it to 15. If I went by 4's, I'd make it to 20, so I'm good on the positives. 4's, I'd make it to negative 20. So my y, I'm going to do by 4's. Then at this point, we're going to go ahead and we're going to graph each point. I'm going to go left by 3, counting by ones, so 1, 2, 3. And I'm going to go down 16, counting by 4's, so 4, 8, 12, 16. Perfect. And I do that for each one of these points. I count to the left and right by ones, so 1, 2, and down by 4's, 4, 8, 12. So somewhere between 8 and 12 is my negative 10. Left 1, down by 4's. 0, it's going to be between 0 and 4 is that positive 2. Count over by 1, up by 4's until I hit 8. Count over by 1's until I hit 2. Up by 4's until I say from 4 to 16. 14 is going to be somewhere in there. And then over 1, 2, 3, up by 4, 8, 12, 16, and 20. So boom, we have ourselves a nice straight line. So we take 2 of the points, and we're going to draw a line. Now what's important is that we kind of extend this line a little beyond the barriers so that we know this graph extends beyond our graph. The arrows tell us that if we wanted to keep this graph going, we could just add more values to our table and we would be perfectly okay. The last thing is we want to label our graph. What is this red line? This red line represents this equation. This equation or this function is called f of x. So right next to one of the arrows, I have stuff written up here, so I'm going to put next to this arrow. I'm going to label this function as an f of x. Other thing that we want to label, and for today I'm only going to be labeling part of them, is anytime it crosses either the y-axis or the x-axis. Now I realize there's 2 here, but I only have 1 crossing on the table, so I'm going to label this one as 0, 2. We would theoretically be able to label this one, but we don't know what that one is just yet. So we're going to save that one for another video. Boom. So let's do another one of those. This one's also called f of x. So I need some values to plug in. So I'm going to say x, y, because I know the fact that my f of x is going to be equal to my y. I'm going to pick some values to plug in. 3, 2, 1, 2, 3. And I'm going to plug them into this expression. So 12 times that thing plus 20, 12 times that thing plus 20, plus 20. Kind of looks like we expanded as we went. and I plug in these values into each one of these blanks. So I plug in the -3, -2, 0, 1, 2, 3. I plug each one of them in. So we work it out. It's going to be a -36 plus 20, which is going to be, let's see, take the difference, which is 16, and keep the negative. I'm going to take -24. I'm going to take the difference, which is 4, keep the negative. Take the difference, which is 8, keep the positive. 20, 32, 4, 56. Perfect. And so we're going to keep all of our x's, and we're going to keep our final values for y. So -3, -2. And I'm going to plug them into my table. Now this time, I know my x's are still evenly balanced on the left and the right because I have -3 and +3 are my largest values. So I can place this in the middle. But what we notice is that I only have 2 negatives, but I have 5 positives, which means I'm going to put my axis a little farther down the graph. And this is going to give me a lot more room for all of these positive numbers, and a little less room for my fewer negative values. Then we're going to do our scales. Our x is fine by ones because I can count to 3 and -3 by ones. My y, however, I need to get to 56 in the positives. So I have 1, 2, 3, 4, 5, 6, 7, 8. So with 8 spots and 56, that should be, if I counted by 7s, that'd be fine, but I wouldn't make it to my negatives. So what we're going to do is we're going to pick a number slightly larger than 7. We're going to say 10s. I know we could theoretically do it by 8s. 10s is going to be a little easier to count, in my opinion. But you can do anything bigger than 7, anything that would fit both a positive 56 and a -16. Let's graph. So count by 1s, count by 10s. So somewhere between 10 and 20, 16. Count by 1s, count by 10s. Somewhere between. Count by 1s, count by 10s. Count by 1s. Ooh, perfect, right on the point there. Count by 1s and by 10s. 30 something. Count by 1s and by 10s. 10, 20, 30, 40 something. Count by 1s. 10, 20, 30, 40, 50 something. Perfect. And so we're going to connect to these points with a straight line that goes just on the edges of our graph. We're going to put arrows on the end that say this graph keeps going if we wanted it to. And I'm going to label this point. So that is my f of x. I see that I have 1, 0, so I know that this intercept is 0, 20. I don't know what this is just yet, but we'll save that for a future lesson. So boom, there we go. Let's try a few more. We have numbers 5 and numbers 7. What I want you to do is I want you to pause the video. I want you to resume it when you're done and see how well you did. And I'm going to put the work up here in just a moment. Okay. So what we see is going on is that we need a value to plug in for first. So I'm going to make myself a nice table. Whatever I plug in, I'm going to plug in into this function right here. So I don't know what values I'm going to plug in. I have to pick those. So I'm going to pick these values, which are going to give me a good image. Now, these aren't always going to be the values we pick.
But for today with linear functions, if you pick some always around the 0, they should give you a good idea. Later on, in different types of curves, in different types of lines, if you have like absolute values, exponentials, or quadratics, you're going to pick a different set of values. But we're going to figure out which values you pick when you get there. For today, we're just going to plug in -3 to 3. So let's see, 2 negatives make a positive 5. That's going to be 2 plus 1, which is 3. 1. I'm taking the difference now. Taking the difference again. And the difference. So I have an XY table that I'm going to create. I'm going to plug in all those X's over there, all the Y's right here. I have an even spread. And here it looks like I have, again, roughly an even spread. So I'm going to put it right in the middle again. My X, we're comfortable counting by 1s. For my Y's, I could make it 5 down, but that 7's going to throw me off, so my Y is going to have to be by 2s. Plot each point, so -3. 2, 4, 6, 7, -2, 2, 4, 5, -1, 2, 3, 0, halfway, 1, negative halfway, 2, 2 halfway, 1, 2, 3, -2, 4, halfway. Perfect. So we have a graph that looks just like this. Just beyond the graph. Put my little arrows that say the graph keeps going. I'm going to label this as an f of x up here. And we also notice that we have 0, 1 as my first intercept. Unfortunately, I don't know what this intercept is just yet. We'll figure that out in a future lesson. Awesome. And the last one. Let's see how well you did on this one. Table of values. I'm going to plug in a bunch of these. Plug each one of these in. And we're going to figure out what they get. So 2 negatives make a positive. It's going to be 5, 0. Oh, now I'm taking the difference. Cool. So once we evaluate that, we're going to be taking those values. Let's simplify our table to make it a little easier to read. Perfect. My x's look good. They're very well balanced, so we can put our axis right here in the middle. My y's, I only have one positive number. I have all of these, so I have 5 negatives and 1 0. So I'm going to put my graph, let's see, way up here. You might be able to put it even higher. I'm going to leave 2 spaces just to be sure. Awesome. My x's are fine. I can count by ones and fit -3 to 3. For my y, see, I need to be able to fit 5 and -25. Well, it looks like these are all multiples of 5, so I'm going to make my life a little easy, and I'm going to say each of these is by 5. So let's do that. Which means left 1, 2, 3, 5. 1, 2, -1, down 5. So it makes it a lot easier to count by 5s when each square is by 5. And then 1, 2, 3 to the right, 2, 5, 10, 15, 20, and 25. Perfect. So you might not have the exact same graph as we have right here, because if you picked a different scale, you might have a different thing. But your graph should be a downward-facing trajectory. Should look something roughly like this. I'm going to say, hey, this is my f of x by this arrow down here. And conveniently, we have our y-intercept right here, 0, -10. And we also have our x-intercept because I have a 0 for my y value right here. So -2, 0. And there we go.